Hello, good evening, everyone. Thank you very much, Richard, for the handover and the great presentation earlier. We're going to give you a bit of a run through from more of a side, which I think is a great contrast from the strategic view. It should give you a bit of an alternative view. As you can see by the way we're dressed, we do spend our time actually on site mostly. So Fresh Heat Networks, we started the company during lockdown. So we're one of the classic lockdown startups. So we started out with a view that we traditionally within the UK make heat networks are quite complicated. Whereas if you go to Denmark and places like that, they're quite the opposite. They're very straightforward, and to a degree, they have the UK is much more contractual when it comes to designing, building, maintaining heat networks. We don't tend to see that much of that kind of contractual, slightly adversarial approach that sometimes happens. So Fresh was launched essentially to help clients make sense of heat networks, as simple as that. We've evolved and it's almost become helping the industry make sense of heat networks, because it's not just clients, it's heat network operators. It's in some instances working with designers to optimize schemes, to get the best out schemes, training maintenance contractors how to maintain this system. So things have really changed these last few years. So very simply, what is a heat network? Well, the government definition for reporting on heat networks is really straightforward, very simple. It's a central plant delivering heat to more than one end user. So 2 houses with a central boiler is a heat network. And if you have that, you are legally bound to report on its performance every 4 years to the OPSS. You must do that. You must submit your form. So we typically have in the UK communal heating, which is a block with a central boiler plant. And we have district heating, which can be 1 or 2 blocks or a citywide scheme, like in Birmingham, in Leicester, Sheffield, Manchester, Gateshead, Newcastle. They have citywide schemes with multiple heat sources going into the heat network. That's probably not the full story. A school is strictly a heat network. Although it's got one end user, it's the same principle. It's got a central boiler plant. It has multiple distribution. It has making sure the heat is delivered correctly in the zones. A hospital is a heat network. Most museums, council offices, lots of office buildings are essentially a heat network under a different guise. So we just need to be wary when we talk about heat networks. We sometimes have a very narrow view, but in reality, it's pretty much any system with a central plant or multiple plant rooms. So when it comes to decarbonisation, we're looking at really to try and assess the scale of the challenge. As Richard said, the challenge is huge. And Richard's already mentioned that 80% of all buildings we'll be living and working in 2035 have already been built. We're living and working in them. So the Royal Academy of Engineers has recently conducted a working group to actually look at the decarbonisation plan for the UK. And Lord Valance, you may remember him from COVID, has basically said we need a radical shift of approach in everything to do with decarbonisation, or we risk not achieving anywhere near the targets that we've set ourselves. And that's straight out of this month's CIBSE journal. Good article in there if you've not read it. So we can't underestimate the amount of work that's required. And Lord Valance basically says it will need the same level of mobilisation as we actually did to get the COVID vaccine out. It almost needs to be a national agenda to get it done. So very briefly, if you speak to cities and countries that are ahead of us in this, like Denmark, their view is just do it, just get it done. Let's stop talking about it. Let's make this happen. Let's get on with it. So what's the goal of decarbonisation? Is it engineering net zero? Is it reducing CO2? It is. It's all of these things, but it's also about making sure that the energy we provide to end users is still affordable. That is low carbon. But I think the real key is efficiency. if 80% of the buildings that we're living in, working and have been built already, when we get to 2035, they're here now, then somehow we need a bigger objective than net zero. We need to do it, as Richard said, efficiently. We need to optimize our heat networks. We need to make sure that when there are district heat networks connecting to areas, that the buildings are optimized and ready for connection to be a positive contributor to heat network, not a negative one. Getting a poor performing building and decarbonising the heat still gives me a poor performing building. So we need to not just look at decarbonisation as a bolt-on package, which I'm afraid in the industry, some people still see I can replace that commercial gas boiler with that heat pump and it'll just work. So it's the bigger picture. So it's about getting to net zero efficiently. It's about having a good plan. So what does a client plan look like? This is from our side, just on heat, not on fabric. We're not strategic view. We're looking at the sort of directly at the heat element of that scheme. So I have a client here, actually based in the West Midlands. They are a housing association. They have 62 heat networks. They have a motivation and a want to decarbonise. They want a strategy. They have an idea of where they want to be. They don't quite understand the stepping stones to get them to their goal. So if they're looking to decarbonise these 62 heat networks over the next 10 years, what's the plan? How are they going to do it? So the simple route is saying, let's prioritise these schemes. Let's look at the 62 and step back and go, whoa, which has got the worst efficiency? And that may be simply gas in divided by the amount of flats to give me an average use. And that gives you a fairly decent metric. But the problem is that you can have new gas boilers on a poor performing heat network and still, surprise, surprise, have a poor performing heat network. So that doesn't tell the full story. Which plant rooms are at their end of life? Straightforward one. Most clients are not aware which plant rooms are at their end of life because they're slightly stepped back and removed from it. So one of the options is to, say which schemes do you know you've got problems on? Which ones are you getting phone calls on every week? Which ones are giving you a big headache? And the only people that will really know that is probably the compliance team, the maintenance team that are involved directly with that input, the old gas team that used to be involved. So we would typically speak to a maintenance contractor and we try and draw up this little shortlist. And we try and whittle that 62 down to about 10. We'd identify which of those plant rooms are at their end of life, and we would then conduct plant room dilapidation. Literally a fly in, have a look at it, and confirm or not if it's on its last legs. Then what we'd do after that 10, we would schedule the other 52 in over the next 18 months, 2 years tops. And what that will enable the client to do is have a budget. And it doesn't become a guess, it becomes a much more accurate budget. So we look at a plant room dilapidation survey here, and I know it's little text, so I'll try and do this laser point. I'll try and be cute here, hope it doesn't backfire. We have our heat emitters at the top, so I have our Hamworthy Pure Well boilers. If you've ever been in a plant room, they're just great big blue boilers. They run for years. They have, they have issues if they're abused in terms of operating them, but they're good boilers. And in this instance, they are 25 to 30 years old. So we have gone in that plant room and we have put here on the right, estimated lifespan left. How much has it got left? And we've done the same for these two clarifiers, MHS clarifiers, the same for the shunt pumps here, the same for the pressurization unit, and the same for the circuit pumps. And we go through the whole asset register and we literally say how long we think it's got left. We will use CIBSE guides on boiler life. We'll also look at the pumps to see if they're being operated outside of their design parameters. So we create this priority list, and the big but is, if we are doing these surveys in September, we will get our reports out in October. The client will deliberate over what to do with them internally and assign a budget. If you're being really good, it's November, December. Then they look at going out to tender. That's a 3-month process, minimum, maybe 4. And that's without design input. This is design and build with a performance spec ready almost. Then that goes out to tender, and we're looking at April, May before tenders come back and get vetted. Then a 3 or 4 month lead in minimum. Oh, we're back to a year from today. So if that priority list includes schemes that are likely to go down in the next 6 months, then we'll be working to get them ready, but they'll be going down most likely before we've completed the process. So you almost have to draw a line in the sand and say, those sites and schemes that are going to go down in the next 6 months, we just have to deal with outside of this decarbonisation plan. Because by the time we get round to doing it, it's too late. And they will all have been replaced with, guess what, gas boilers. Because it's now become an urgency. It now needs doing, not next year, but today. And we have surveyed schemes and gone through that. So we've worked on 150 decarbonisation studies in the last 18 months. Probably a similar amount of optimisation studies on big district as well as small communal. And it typically takes a year from that survey for action on site. So we just need to bear that in mind. Our job is to identify the barriers to decarbonisation and to come up with some, proposals based upon how we see it on that scheme. So the key element in any heat network, I don't know whether anyone's ever heard of this before, hierarchy of heat. I remember getting shouted down about 10 years ago when I started talking about this. I was told it was the wrong way around and the plant room is at the top. So what this triangle basically says is that the highest efficiency gains on a heat network are governed by the amount and the control of the heat delivery within the zone. So I want to generate as much energy as possible to meet the actual demand. I want to just meet the demand. I want to distribute it to the zone as efficiently as possible with losing as little heat as possible and deliver as much of the heat in the zone and send back as little unused heat back to the plant room so that the whole cycle can start again. That's why heat networks are typically designed at a 20 to 30 degree delta T, because I'm delivering heat. I'm not sending it round and bringing it back unused. So that level of control you have over in the flat is vitally important. The plant room sends out what it's told, but it gets back what it's given by the sum of the heat delivery. So flats, heat zones first, whether it's a museum or a classroom or a hospital, the heat delivery hierarchy of heat is the same. The zones are the ones that really count. So if we're on a scheme, we're identifying barriers to heat delivery. The first thing we look at here on the left is the delta T at radiators or fan coils or trench heating. And in this instance, we have a 0.8 degree delta T on this radiator. It will have been designed at 20 degrees delta T. So if I'm getting 0.8 at the radiator, how am I going to get 20 degrees back at the plant room? If I'm not delivering heat in that zone, I cannot achieve my design temperature. I am sending around too much heat and I'm not delivering it. And one of the symptoms on a radiator here on the right is CP1 Code of Practice for heat networks. Basically says that you should have presettable radiator valves. You shouldn't be setting them on a lock shield and trying to balance them because there's no linear travel. You really cannot balance them using a lock shield. You use a presettable valve, calculate the setting, and what that basically does is allow a set flow rate through. And it will give you your delta T. You still need to check it. In this instance, it's been specified presettables, and you've got them. This is our Drayton TRV4. What you can't see is here, is it's set on its factory setting number 6. It's never, ever been set. It's been put in because it's in the spec, but it's never been set. And that is the case time and time again. So that gives us inefficient heat delivery. A few of the other barriers, if I have clarifiers or HRUs, my design flow rates at the taps will be based typically 8 to 12 litres a minute. That tap there is running at 24 litres on the left. If I'm using an HRU, I'm using possibly 3 or definitely 2 times the amount of kilowatts that my whole hot water diversity has been calculated on. So at peak, if that's set like that, the whole system falls. And that is basically at commissioning point. It needs to be set correctly. There's another barrier to decarbonisation here in the middle. It's uninsulated primary pipework. And in this instance here, we have here on the left here a bypass, so that when the heating and hot water in this instance is satisfied, it runs back round in a bypass. So if my pumps are looking for an increase in pressure to reduce their pumping speed, it can't pick it up because it's still whizzing around the bypasses. It can't sense a change in demand. And finally, in a flat, we have micro bore pipe here. That quite a lot. If I'm looking at operating that flat and that heat network at 55 or so degrees, I can no longer get the flow rate through that pipe to give me the heat output at that radiator. The lower the temperature, the higher the flow rate to deliver the heat required. So these are common barriers that we see, and our job is to identify these because we want an efficient heat network that's decarbonised, not just a decarbonised heating system. Two different things. We look at distribution, which is the pipework that connects the plant room to the heat delivery zone. A classroom, a ward, a flat. The material, it's the same. In this instance here on the left, we have a double regulating valve, and it's being used as a bypass. So when the heating zone stops calling for heat and there is no flow, it allows a route back from the primary flow around and back to the boiler. And that's fine, as long as it's sized to meet the minimum flow rate of the pumps. In this case, it's not been set. It's fully open. And we have 10 floors here on this building, and we have 2 of these on each floor. So I have 20 of these, and each one is bypassing 1,000 litres an hour. So water takes the least line of resistance. It won't always go through there, but these are permanent flow bypasses. So it's a major, major inefficiency. I'm looking for my pumps to sense a change in demand, either increase in pressure with less demand, decrease in pressure with more demand, and modulate accordingly. If they can't sense that pressure change, they can't change. So what do? They just keep going flat out, which means I get no heat delivery because I'm sending water around too quickly. I get a narrow delta T, and guess what the maintenance contractor will do if there's a problem? Speed the pumps up even more. So our goal is to look at these barriers and come up with a list of them that ensures that they are done as part of any enabling works for decarbonisation. Can't just bolt the stuff on. So very simply, the whole issue, the biggest issue and the biggest barrier to decarbonisation is that there is no conversation between energy supply and energy demand. Typically, what we're looking for is a demand-driven system, that the energy production matches as near as possible the energy requirement in the zone. Unfortunately, we see energy production here and we see actual real demand. The moment it goes above the level, it all works. But what we find is as demand starts dropping from peak load, which is 2 or 3% of the time, we find the primary energy just keeps plugging away. So we have this out of kilter balance. Now here's the scheme here, and on the left you have the primary flow temperature, and I have set these red, amber, green bands on this bit of software. So there's my red zones, and my green zone is 62 to 74. My return temperature in the middle there, my green zone is 40 to 55, and my delta T is the design, 20. This is an average over 7 days, and my average, not worst, average delta T is 1.1 degrees. So what does that mean? Very simply, if I design a boiler, if I look at boiler manufacturers' tables for kilowatt output and flow rate, I require a flow rate of 1 to deliver 20 degrees. Just pick a number. At 11, I now require a flow rate of twice that because I'm not delivering heat, so I need to send even more through. At 1 degree, surprise, surprise, it's likely to be 3 times the volume of water running around the heat network, not being delivered. Extra pumping costs, heat losses. My boilers are never likely to condense. They won't condense at 67, they'll condense at 55. So we're compounding things. So we really need to look, when we do decarbonisation of legacy schemes, the 80% of the schemes that will be there in 2035, is we look at heat delivery. Now, I'm not going to explain this in too much detail. In the middle, I have my primary flow from my boiler, and she's left to the south tower, right to the north tower, and each goes through the heat exchanger, down the bottom and back out. On the right and left sides, I have the actual circuits going to the flats in this instance. So I have my primaries in the middle, my plated heat exchangers, and my secondaries to the left and right. My eyes go to the middle. On the south tower, I'm getting less than 1.5 degrees delta T. I'm oversupplying heat and I'm under delivering it. On the north tower on the right, I'm getting 11 degrees. That's far better. Something different's happening there. I'm not quite where I want to be, but with a bit of tweaking, I think we can get there. The key element is in the middle. Here, I am oversupplying heat by about a factor of 3 to these plates from the shunt pumps on the boilers. And on the left, I'm oversupplying heat on the secondary circuit on the south tower by a factor of 3 again. So we can put a decarbonised heat source on here, but it will not alter this. We need to look at the zone. So what other factors are involved? Pumps on the left there, set on manual maximum. I don't know whether anyone's ever used the Grundfos dongle. Grundfos make a little pump dongle. It's about £150. If you see a pump with this little Wi-Fi type symbol, you can actually put it on top, pair it up with your phone, and it'll give you a full-on pump report. Operating hours, am I getting pump rotation, that kind of thing. So here we have a Grundfos pump capable of being controlled any way you wish. In this instance, it's on constant, and the external analog input is not enabled. So on a heat network, I want my pumps in the plant room, primary or secondary, after a heat exchanger, to just deliver me enough heat and flow rate to the furthest point away. And at that point, I'd like a sensor, a differential pressure control sensor on that circuit furthest away, set to the correct differential pressure for that zone. So if it's a flat and I've got a heat interface unit, that will need a minimum of 50 kPa pressure drop. And if my sensor is 2 or 3 flats down the corridor on the riser, I probably need to set that to 65 kPa to make it work. So as long as I have 65 kPa or 50 at that last HIU, I must have it everywhere. Very simple method of control. If I control to the worst case scenario, I get control over everything. And all my HIUs just work. They light up because they're working within their ideal operating zone. So pump control is major. Also water quality. We have poor water quality, and if we're doing a decarb survey, we're really interested in what lifetime is left in the pipework that's in there. Do I need to replace all the risers, for instance, all the laterals? So just a simple water sample will give us that information that we need. So what do we do with this once we get this information? We come up with options. So we look at feasible air source heat pump locations, where the plant room is. We look at, can we get a shared ground loop array or a central ground source heat pump? And we're really just looking to formulate a proposal to the client in a hierarchy of feasibility. Typically, that will be air source heat pump with a hybrid. In reality, very difficult to do because I have high return temperatures. If I haven't got my system balanced, I do not want high return temperatures coming back than my heat pump is then producing. So I need to be very careful on control on hybrids. We look at low temperature, high temperature heat pumps. We look at, can we change clarifiers over to water storage air source heat pumps? You can get 400 litre water storage units with an air source heat pump in it. So you could just keep going on to clarifiers and start that journey if you wished. One that's becoming increasingly popular, second from the bottom, the shared ground array, typically Ken's a shoebox or similar. We're finding a lot of clients are going down that route because there's diversity, because every flat has an individual heat pump, but a shared array. And what that means is I haven't got 4 big heat pumps doing a development. I've got 200 doing it. And not all of them are going to be calling at the same time. So my electricity loading is different. And the difference is this. With that kind of system, I connect and notify the local power network company. With 4 big heat pumps, I have to notify before I connect. And the substation may take a year or 2 to upgrade in London at the moment. Whereas the reverse is the case with the smaller ones. We also look at phase change material. If anyone's ever used those little hand warmers, we press the button. Believe it or not, you can run heating systems off bigger versions of those. Most clients are not quite going for them yet. They're not quite sure because they've not rolled out. There's not that much experience in the UK, but it's an option. So the next steps is to provide a costing proposal, include carbon savings. So typically, looking at one here, this is an air source heat pump option, and we've taken some advice on this, and we've come up with carbon calcs. As Richard said earlier, it's invariably more expensive. It is invariably more expensive operating a low carbon heat source. Gas, I'm afraid to say, and I know it's all relative, but compared to electricity is really cheap because of the carbon content of electricity that's still built in and all the cost elements. If you compare the two, they don't bear comparison. So at the moment, it's higher. That may change. It needs policy change to make that happen. We also look at a shared ground array. So here's a typical ground array. We have a full quotation. In this instance, it was a supply and fit. And some clients actually like the shared ground loop because there's an option to finance the ground array element of it, separate from the actual heat pumps within the flat. And that way, it's more cost effective than shelling out the full capex in one go. Also, it makes meter and billing simpler. It's just one electric meter. So it is an option for some clients. So to summarize, we're more the boots on the ground side, we're more the site side. Our role is simply to provide guidance. We're not here to make a decision. We're here to take a holistic view of the heat network, take a step back from looking at product to looking at the whole heat network. It's really important from our view. We're trying to provide them with enough evidence so they can become what we call an informed client. And typically, we will then get involved in the next step, which would be appointing principal designers. You may see us, you may not, but at some point we'll be looking at your proposal, whether we are visible and published support partners or we're sitting behind the scenes. And like it or loathe it, you're going to see a lot more of this. There's something coming out next year. Next year is a massive year for heat networks. You have Ofgem regulation coming out. You have heat network zoning, where you will be mandated to connect in certain areas. And you have heat network technical assurance, which basically means you'll need a heat network assessor to sit with you every step of the way that says to you, great design on there. Could you just tell me why you've used 65% as your heating diversity? Because that's right on the knuckle. Is there any reason why you've gone with that? Could you tell me why your velocity on your copper pipework is 1.6 meters a second, when for that size it should be 1.5? It's close, but have you thought about that? That'll go right through to acceptance testing the finished heat network, and unless it is signed off, you cannot switch it on. You will not be able to switch it on. You will need authorization. So this checking and compliance is a good thing, because at the moment there are heat networks that are not performing brilliantly. And what this will do is assign a process and hopefully give us what we all want, which is the heat network that the client and their customers need, which may have been slightly different than what they've been given previously. Funding options are available. As Richard says, there's HNES, the Heat Network Efficiency Scheme. We've been involved in 50 or 60 of those. There's PSDS, again, around a similar quantity, 50 or 60. They can be used on, HNES can be used on district schemes as well as communal. And they can, believe it or not, be used to study the enabling works required in a scheme to get ready for decarbonisation, but not the decarbonisation element. You'd be glad to hear. That's me too. Anybody got any questions, please?